Welcome back to Math 104. We continue our study of the game of rolling a pair of fair dice 3 times. On each roll, either the sum equals 8 or it doesn't. If it does, you win that roll, and if it doesn't, then you lose that roll. So you can win more than once when you play 3 times. You can win 0, 1, 2, or 3 times when you play 3 times. Our first task is to understand the breakdown of an ideal data set of 36 cubed, which is 46,656 numbers of wins, in this experiment. There are 3 choose 0 times 5 over 36 to the third power times 31 over 36 to the 0 power, so the probability of getting 0 wins, times the total number of outcomes in our ideal data set. That turns out to be 29,791 zeros. Of the 46,656 numbers of wins that constitute an ideal data set, this many, just under 30,000 of them, are zeros. We computed in the last video that there is about a 63.85% chance of getting 0 wins in 3 rolls of the dice, and therefore 63.85% of the total number of outcomes in the ideal data set equals this many outcomes, 29,791 of them, that are zeros. This is the proportional share of zeros corresponding to the likelihood of getting a 0. Similarly, by exactly the same approach, the probability of 1 win, so 3 choose 1 times 5 over 36 to the first power times 31 over 36 now squared, so 1 winning roll, 2 losing rolls, times 46,656. So this is a certain fraction, a certain percentage, just under 30% of all the outcomes should be 1s. That turns out to be 14,415 1s. The number of 2s in the ideal data set is found in the similar way. The probability of 2 wins, 1 loss in 3 rolls times the total number in the ideal data set. Now that's just 2,325 2s, so this is only about 5% of the total, as we computed earlier. That works out concretely to be 2,325 2s in our long list of numbers. And finally, the number of 3s is going to be very small. That's only 125 3s. We figured out earlier there was less than a 1% chance, well under a 1% chance, of obtaining a winning roll all 3 times. Out of a perfectly representative 46,656 runs of the experiment, or a tournament attended by 46,656 people, which is perfectly representative of the long term, 125 of those people, precisely 125 of them, will win all 3 times. All of that was mostly to refresh our memory about what ideal data sets are and what they mean. Now let's use what we just found to compute the expected number of wins in this same game. That means we're averaging up a large set of numbers, specifically 46,656 of them. I'm going to add up 46,656 numbers and then divide by how many there are. No one's expecting you to write out all of those 0s and 1s and 2s and 3s separately. The idea here is to group them. You have the number 0 a certain number of times. So you're adding up a certain number of copies of 0. In particular, 29,791 of them. You're also adding up a certain number of copies of the number 1, namely 14,415 of them. You're also adding a certain number of copies of the number 2, namely 2,325 of them. And finally, you're adding up a certain number of copies of the number 3, namely 125 of them. When you compute this, you end up with 19,440 divided by 46,656. So right there we can see that this is going to come out to be something less than 1. It will turn out that if you go and reduce this, it's exactly 5/12ths. This is approximately 0.4167 wins. This is the expected number of wins computed by the ideal data set method. It's exactly the same answers we got using the weighted average approach. Either way, this was a fair amount of work. And that was the point. If you thought that this was a pain in the neck, excellent, that was correct. because the other reason for going through these laborious computations was as a setup for the following wonderful shortcut. A very useful shortcut for computing expected values, but only for the expected number of quote-unquote successes in a certain number of independent Bernoulli trials, is the following. If you perform n independent Bernoulli trials, each with probability of success, little p, then the expected number of successes equals n times little p. That's all you have to compute. And this actually makes conceptual sense. If I flip 1,000 coins, and each coin has a 70% chance of heads, it makes sense that on an average day of flipping 1,000 of those coins, I would obtain 1,000 times 0.7, which is 700 heads. 1,000 coin flips, each with a 70% chance of heads. On average, I should expect 700 heads. Maybe I'll get fewer, maybe I'll get more, but it makes a certain amount of sense to say that 700 is the expected number, or the average number. Equipped with this wonderful shortcut, now let's take a second look at our die rolling game. So this is the same game where you roll a pair of fair dice, and either the sum equals 8 or it doesn't. And that probability that the sum equals 8, that's our little p, that's 5 over 36. So this right here is our little p. We're looking at playing 3 times, so that's our capital N. According to our formula, the expected number of wins, the expected number of successes in 3 Bernoulli trials with a 5 over 36 probability of success on each trial equals n times p, which is 3 times 5 over 36, and after you simplify, after you cancel a 3 from numerator and denominator, that's just 5 over 12, and that's the expected number of wins. That's the average number of wins. We get exactly the answer that we're supposed to, and with much less work. But let's not get carried away and start applying our shortcut to problems that it actually doesn't pertain to. For example, here's an important contrast. In the same die rolling game, where every time you play, you roll a pair of fair dice, if the sum equals 8, you win that roll. So it's exactly the same game, but now we're introducing another layer. Besides this issue of how many wins, there's now going to be a question of how many dollars. So suppose that you play 3 times. If you win all 3 times, you receive $100. If you win only 1 or 2 times, nothing happens. And if you don't win any of your 3 rolls, then you lose $1. There is no entry fee to play this game. These are the only dollar amounts that are involved. We can ask, if you play 3 times, what is your expected gain or loss in dollars? That is a different question from what is your expected number of wins. That shortcut only applies to the question, what is the expected number of wins? What is the expected number of successes in so many Bernoulli trials? Whatever's being counted as a success, if you're asking how many of them there are, then you can use the shortcut, but otherwise not. Since we can't use the n times p shortcut here, we have to compute the expected value in the usual way. Let's use the second method, the weighted average approach to computing expected value. So we need to take each possible dollar amount that we could gain or lose in this game, with a plus or minus in front of it, according to whether it's a gain or a loss, and multiply that dollar amount by the probability that we will gain or lose that dollar amount. So we have $100 times the probability of gaining $100. Just for good measure, I'll write this out in full, plus $0, that times the probability of a $0 gain. That, of course, is going to contribute 0 to the whole sum. We don't really have to write it, but just for completeness, I'm putting it in. Plus negative $1, that's the $1 loss, times the probability of a $1 loss. If we'd been asked to compute the expected number of wins, we'd be taking each possible number of wins times the probability of that number of wins. Instead, we are asked about the expected gain or loss in dollars. So we have to take the number of dollars gained or lost, and multiply each number of dollars by the probability of gaining or losing that number of dollars. Whatever kind of value we're finding the expected value of, those are the values that need to be multiplied by the probabilities of obtaining them. That equals $100 times, well, what is the probability of a $100 gain? That's exactly the probability of 3 wins and no losses. So 3 choose 3 times 5 over 36 to the 3 times 31 over 36 to the 0. Plus, well, this one we're just going to dismiss as 0. We don't need to write anything else for it. It's going to be 0 times some probability, which will equal 0. Plus, negative $1 times the probability of a $1 loss. Well, how do we achieve a $1 loss? That means 0 wins and 3 losses. So we're multiplying by 3 choose 0 times 5 over 36 to the 0 times 31 over 36 to the 3rd. Each dollar amount that we could gain or lose has been multiplied by, that is, weighted by, the probability that that's what happens. It's helpful to see what these probabilities are, and not just skip to the final answer. $100 is being weighted by its very low probability of occurrence. So $100 is weighted by 0.0027, while negative $1, that $1 loss, it's such a small loss, but it's very likely. It's weighted by 0.6385. When you put all this information together that weights each possible dollar gain or loss by its likelihood of occurring, this turns out to be approximately a 37-cent loss. In other words, in the long run, this game is a losing proposition. In the long run, on average, you are losing 37 cents for every 3 plays of the game. When dealing with these expected value questions, we have to stop and think, is this a job for the n times p shortcut, or is it not? Here's another example. Let's see whether the n times p shortcut applies or not. Each person in a certain state has, independently, a 10% chance of having had the flu in the past 5 years. Okay, we're just supposing that this is actually the case. If 1,000 people in this state are surveyed, how many do you expect to have had the flu in the past 5 years? So stop and think for a minute. Is this a job for the n times p shortcut, to find the expected number of people who have had the flu? Or is it not a job for the n times p shortcut? Well, I'm happy to tell you that it is a job for the n times p shortcut because of what value we're finding the expected value of. The Bernoulli trial is to ask each person, have they had the flu or have they not had the flu? And because of the way this is phrased, we can think of having had the flu as being a quote-unquote success, with little p equals 0.1, and not having had the flu as a quote-unquote failure. Right? It doesn't matter whether it's what you actually think of as a good thing when we use this word success. That's why it's always in quotation marks. So this is a Bernoulli trial, and we're performing 1,000 independent Bernoulli trials. Furthermore, we are asking the expected number of successes in 1,000 trials, or we're asking the expected number of times that the Bernoulli trial turns out one way, as opposed to the other way, in 1,000 trials. Since we're asking that most basic question about 1,000 performances of this Bernoulli trial, it is a job for the n times p shortcut. We're asking for the expected number of successes. If each person who had the flu missed a certain number of days of work or school, and then we were asking what's the expected number of days of work or school missed, that would be a different kind of a question. But we're asking the most direct question that's directly in terms of the same thing that the Bernoulli trial itself is in terms of. So it is a job for the n times p shortcut. N equals 1,000, p equals 0.1, and so we expect 100 people on average to have had the flu in the past 5 years in that state. Before going on to the next video, answer the following question. Each computer from a certain manufacturer has a 95% chance of working properly, independently of the other computers in the same shipment. Each properly working computer will result in a $100 profit for the manufacturer, but each defective one will result in a $50 loss. The question is, how many computers do you expect to work properly in a shipment of 200 computers? First think whether this question can be answered using the n times p shortcut, or whether it can't be solved that way. Either way, apply the appropriate method for solving it.